Hi guys, my name is Matthias Calderon. I'm an aerospace engineering student at University of Maryland, and today I'm going to talk to you guys about the needle nose pliers, and more specifically about the mechanical advantage that we get from them. So guys, needle nose pliers are a really great tool. They've got a lot of uses. I use this pair to get hooks out of the mouths of fish, but it's not the only thing. Some will have wire cutters or wire strippers for electricians' work. You can bend wires and grab things in thin areas. So yeah, they've got a lot of uses. So we're going to get into finding the mechanical advantage of the pliers, and to do that we're going to start by modeling the forces. So we're modeling the forces here. We're going to have, of course, the input force coming in. We'll call that F handles. That'll be on both of the sides here. Then we're going to have force from the jaws of the plier. We'll call that F jaws. It's going to be here and here. But to model the pin forces, we're going to have to split this in half. So when we look at, I've kind of taken out this area here and split it up into the two different assembled pieces. At the pins, we're going to have a reaction force in the Y direction as well as a reaction force in the X direction. So now that we've modeled the forces in the pliers, I've added some dimensions, and these aren't random. They're from the Klein Tools 6 5/8 inch needle nose pliers. They're the example that I used in my paper, so I continue to use them here. As you can see, we're going to need to come up with an F handles value. We're just going to say that we're exerting 40 pounds on the handles of the pliers. So when you already have the F handles force of 40 pounds, it's pretty easy to solve for the force from the pliers. You can just do the moments at B. And for 40 pounds, you're going to get a F pliers force of 61.3. For mechanical advantage, you're going to do the 61.3 pounds over the 40 pounds, and we're going to get this number here, 1.5325. There's no units to this number. I'd think of it as a ratio. For every amount of force you're putting in, you're getting 1.5325 times that amount of force out. So the fact that this is a ratio between the output and input forces is good. It means that this 40-pound force that I just seemingly came up with out of nowhere, which I actually did come up with it out of nowhere, but it means that it doesn't matter. The ratio will stay the same regardless, whatever that value is. So in this video, what are we covering from our mechanics class? Well, as you can see, we've got our free body diagrams here, so we're covering equilibrium. We've got force vectors, moments in solving for the F pliers. We are also using machines. If you see here, when we model our reaction forces, we're modeling them equal and opposite on the two different free body diagrams for the two different parts of the assembly. So what kind of tests, what kind of experiments can we do with this information? Well, during my project, I learned that if we kept the length of the jaws constant, as the length of the handles increased, the mechanical advantage of the pliers would also increase. In fact, I actually found that it was directly proportional. When the length of the handles was doubled, assuming the length of the jaws kept the same, the mechanical advantage would also double. This follows that it would be the inverse for the length of the jaws. So something you could test here is, for example, applying different lengths of handles to pliers and determining what their mechanical advantage is. So I wanted to talk to you guys today about mechanical advantage because I think it's so important to understand the advantage our tools give us as engineers. We have to understand the limitations we have, and they're just a cool tool. They have so many uses, like I said before, and go out and buy some. They're awesome.